You ever look at molecules and wonder how? How does nature build these perfect, symmetrical shapes from, a bunch of tiny little atoms? It really is a chemical puzzle. So let's dive in and see if we can solve it. So here's the big question we're tackling today. How do simple atoms, like a single carbon atom, manage to form these complex, perfectly symmetrical molecules? It's not magic, I promise you, it's chemistry, but it definitely feels like a mystery that needs a solid explanation. All right, our first clue comes from an atom's outermost electrons, the ones doing all the work to connect with other atoms. These guys are called valence electrons, and they hang out in specific regions of space called orbitals. Now, a really early idea, called Valence Bond Theory, suggested something pretty simple. Atoms form bonds by literally overlapping these orbitals, kind of like holding hands to link up. So what does that overlap actually look like? Well, you can see here, you might have a round s orbital overlapping with another s orbital, or maybe with one of these dumbbell-shaped p orbitals. The key thing to notice is that different starting orbitals should, logically, create different kinds of bonds. Makes sense, right? Okay, so let's put this theory to the test with a classic molecule, methane, CH4. That's one carbon atom right in the middle, bonded to 4 hydrogen atoms. Now here's the catch. Carbon's valence electrons aren't all the same. They live in 2 different types of orbitals, one round s orbital and 3 of those dumbbell-shaped p orbitals. So if we follow the logic of our valence bond theory, we should totally expect 2 different kinds of bonds in a methane molecule. One bond made from carbon's s orbital, and the other 3 made from its 3 p orbitals. Seems straightforward enough. And bam, this is where the theory just completely hits a brick wall. The prediction is a lopsided molecule with unequal bonds. But the experimental reality, what scientists actually go and measure, is that all 4 bonds in methane are absolutely 100% identical. Same length, same strength, everything. Our simple theory just failed. And you know what? This is what science is all about. When a theory doesn't match the evidence, we don't ignore the evidence. We find a better theory. So the question becomes, how do we fix this puzzle? How does carbon make 4 identical bonds when it starts with 2 different kinds of tools? To figure this out, let's forget about chemistry for a second and talk about ice cream. Imagine you've got 1 scoop of chocolate. That's our s orbital. And 3 scoops of vanilla. Those are our p orbitals. If you try to give these to 4 kids, they're going to fight over that 1 chocolate scoop, right? So what's the solution? You dump all 4 scoops into a blender, whiz them up, and what do you get? 4 new identical scoops of chocolate vanilla swirl. Now everyone's got the same thing, everyone's happy. Well, that blending process is exactly what atoms do. It has a fancy name, hybridization. It's this incredible concept of mixing up atomic orbitals that have similar energy levels to create a brand new set of totally identical or hybrid orbitals. The atom is basically its own little ice cream shop, making perfect chocolate vanilla swirl orbitals whenever it needs to form bonds. Now, there are a few key rules to this whole hybridization game. First, the number of orbitals you put in is the number of hybrid orbitals you get out. Simple. Second, these new hybrid orbitals are all identical in shape and energy. Third, and this is huge, they form stronger, more stable bonds than the original pure orbitals ever could. And finally, they automatically arrange themselves in space to be as far apart from each other as possible, and that right there is the secret to creating those perfect geometric shapes. So you can basically think of hybridization as a set of recipes. Mix 1 s and 1 p orbital, you get sp hybridization, which makes a perfectly straight, linear molecule. Mix 1 s and 2 p's, that gives you sp squared hybridization, and you get a flat triangular shape. And for our old friend methane, you mix 1 s and 3 p's, you get sp3 hybridization, which gives you that beautiful, perfect tetrahedral shape. And there you have it. The whole point is that this elegant theory of hybridization perfectly explains how all these complex, beautiful 3D shapes just emerge from these simple rules. It's not random at all. It's the direct result of atoms mixing their orbitals to get the most stable arrangement they possibly can. And listen to this. This quote from our source material really just nails it. The shape isn't some accident. It's a direct consequence of hybridization. And the predictive power is just incredible. If you can figure out the hybridization, you know the shape, period. And believe it or not, it gets even cooler. The theory doesn't stop with just s and p orbitals. For bigger atoms, their d orbitals can jump into the mix, creating even more complex and honestly really beautiful geometries, like these trigonal bipyramidal or octahedral shapes. The same basic principle just keeps on expanding. Okay, so at this point, you're probably thinking, wow, this is really cool, but do I have to go back to the electron configuration every single time I want to figure this out? And the answer, thankfully, is no. There is a fantastic shortcut. And here it is. It's so simple. All you have to do is calculate a number we're going to call Z. And Z is just the number of sigma bonds. Those are the direct head-on connections between atoms, plus the number of lone pairs, which are those valence electrons just hanging out on the central atom, not involved in a bond. And once you've got your Z value, the rest is just a lookup table. It's that easy. If Z equals 2, the hybridization is sp. If Z equals 3, it's sp squared. And if Z equals 4, you've got sp3 hybridization. This one little number tells you everything you need to know. Let's actually put it into practice right now with a water molecule, H2O. So the central atom is oxygen. How many sigma bonds does it have? 2, 1 to each hydrogen. And how many lone pairs does it have? 2 of those as well. So what's Z? It's 2 plus 2, which is 4. And what does a Z value of 4 mean? It means the oxygen in water is sp3 hybridized. See? It's that simple. So we've cracked it. Hybridization gives us a beautiful explanation for the geometry of the electron orbitals, how they spread out to minimize repulsion. But wait a sec. If you think about that water molecule, 2 of those sp3 orbitals are holding lone pairs, not atoms. So what does that do to the final shape made by just the atoms themselves? Well, that's a puzzle for another day.